Welcome to this introduction to gradient descent, a cornerstone optimization algorithm in machine learning. To understand gradient descent, imagine a graph like this one. The x-axis represents parameters, and the y-axis shows the loss associated with those parameters. Here, we add a loss function, a curve that tells us how good or bad our parameter choices are. Our goal is to reach the lowest point on this curve, where the loss is minimized. Now, let's see gradient descent in action. We start here at a high loss value. The algorithm takes small steps, following the slope of the curve, gradually moving downward. This point here is the minimum. It represents the best set of parameters with the lowest possible loss. Now that we've seen the basics of gradient descent, let's dive deeper into how it calculates these steps. Stay with us. In this scene, we'll explore the concept of a loss function, a fundamental building block in machine learning. Let's begin by plotting a simple quadratic loss function. On the horizontal axis, we have the input values, and on the vertical axis, we measure the loss or error. This blue curve represents the function f of x equals x squared plus 2. Notice its parabolic shape, which is common for loss functions. The most important feature of this curve is its lowest point, or minima, which we've marked here. The minima represents the point where the loss is smallest, meaning our model predictions are closest to the actual values. In essence, the loss function quantifies the difference between what our model predicts and the actual observed values. By minimizing the loss, we improve the accuracy of our model. So to summarize, the loss function helps us measure prediction error, and its minima is the optimal point we aim for in machine learning. Let's move on to see how this connects to gradient descent. In optimization, we often deal with a loss function like this one, where the x-axis represents a parameter and the y-axis represents the loss. To understand gradients, let's highlight a specific point on the curve and examine its slope. At this point, we draw a tangent line. The slope of this line represents the gradient. The gradient vector is represented as this arrow. Notice how the gradient vector changes magnitude and direction as the point moves along the curve. As you can see, the gradient is a powerful tool in optimization, guiding the path toward the minimum of the loss function. The first step is initialization. We start with an initial guess for the parameters, denoted as theta naught. Next, we calculate the gradient of the loss function with respect to the parameters. The gradient tells us the direction of steepest ascent. Using the gradient, we update the parameters. This brings us closer to the minimum of the loss function. Finally, we repeat these steps iteratively until convergence. This is the essence of gradient descent. This concludes the explanation of the gradient descent algorithm. In gradient descent, the learning rate plays a crucial role in determining how optimization progresses toward minimizing the loss function. To understand this better, let's compare two scenarios, a high learning rate on the left and a low learning rate on the right. In the left graph, we simulate a high learning rate. Notice how the optimization takes large, erratic steps. This behavior causes oscillations, and in some cases, it might never converge to the minimum. Now, observe the right graph. With a low learning rate, the steps are much smaller and more controlled. While this ensures convergence, the process is significantly slower. Let's compare these two behaviors side by side. Notice how the high learning rate oscillates wildly, while the low learning rate converges steadily, but slowly. The learning rate is a balancing act. Too high and you risk instability. Too low and the process becomes inefficient. Finding the right learning rate is key to effective optimization in machine learning. Now, let's explore the different variants of gradient descent, each suited for specific scenarios. On the left, we have stochastic gradient descent, or SGD for short. And on the right, minibatch gradient descent. First, let's look at SGD. In this method, parameter updates occur after evaluating a single data point. Now, compare this to minibatch gradient descent. SGD is noisy but quick, while minibatch strikes a balance between speed and stability. In practice, the choice depends on your specific use case. Minibatch is often preferred for its balance, but SGD can be useful for large datasets. Gradient descent. Conclusion and applications. Gradient descent is a powerful optimization algorithm that lies at the heart of machine learning. For neural networks, gradient descent adjusts the weights and biases to minimize the error during training. In linear regression, gradient descent finds the best fit line by minimizing the sum of squared errors. For logistic regression, gradient descent optimizes the sigmoid curve, enabling accurate binary classification. And beyond machine learning, gradient descent is used in general optimization problems, like finding the shortest path or maximizing profits. Each of these examples demonstrates the versatility of gradient descent. In summary, gradient descent is a foundational tool that empowers us to solve complex problems across diverse domains.